on to the action.
Good afternoon. Thank you all for this invitation from the organizers. One of the thanks to my co-authors was for we have 2 valuable talks. I want to point out that it does involve collaboration across many groups, many labs. You can use the facilities that we have introduced in microscopy, assembly, grows into these things from Catalysis, development, excess. Hansen was relevant, we talked about multi-levels, we use low multi-levels in our work as well. We've done some DFT work in collaboration with Burt and then GM has been exploring this work through collaboration support of that. I want to thank Rostrup-Nielsen for wonderful interactions that I had over the years. The last meeting was in October in Beijing, and that is the air quality in the back in Beijing. And there was a hotel. That's actually a hotel. The APEC summit was to be held, and all the world leaders were going to come there. And you could barely see it from where we were standing. But I met this first time in my first visit to other also on sabbatical, and he was the director of R&D I think that time. And we talked about what problems could be of interest, and he certainly had a big role in telling me that I should study catalyst stability and stimulants. So we started working on that, and over the last 15 years we've been doing more and more work and getting better. I hope that we can show you some of this. Now I think we have to move it to the right. Okay, so here's, you heard from Hans about how it's important to do research that's relevant and relevant to industrial needs. And here is an industrial need. Cars are changing, the EVs are becoming more efficient, so the exhaust temperatures go down. And with all of this temperature, they don't have enough energy to do the catalysis. And there are hybrid cars that go on and off, so the catalysis doesn't get as hot. So here he has set up a challenge that the majority of the breakage should be eliminated by 150 C. But remember, in many cases, these catalysts go at high temperatures. So the challenge is how to keep the catalyst stable and still radioactive at lower temperatures. Now, palladium is used in these demonstration catalysts. What's remarkable about palladium is, if you look at this light-up curve that I brought from Chan Kim, who used to be a GM, provided on this project, this was really a time oscillation. And what it shows is that the platinum light-off, or the palladium light-off, is not as low a temperature as platinum palladium. So the first thing you learn is that the platinum palladium catalysis is good from the catalytic standpoint. So what's more remarkable is that in this case, the 2 catalysts were physically mixed. So they made platinum aluminum, they made palladium aluminum, they just mixed them and aged them at 750 C. So to learn, we're following this phenomenon of self-assembly. We want to understand better how exactly does self-assembly happen in the real formula catalyst. Furthermore, we move from Ford, particularly George Brown, which tell us that added palladium improves the stability of the catalyst. And this is what happens. If you take platinum and you age it at a very high temperature in air, the particle size grows enormously. By about 900 degrees, you will see 100 nanometers and larger, even we see sub-micron particles. So platinum ages severely under oxidizing conditions. But if adding palladium, this is the 50-50, you arrest the growth of particles. So you have to make the catalyst more stable. And the question is, what exactly is the role of palladium in these catalysts? So this, I just wanted to illustrate to you this phenomenon of self-assembly. So this is the textile universal life sizes, and I don't need to convince you that by 900 degrees, difference between the platinum and palladium. And I'll show that to you. But the lower band shows it's not as significant. What's more interesting is what happens to the catalysis is heated at higher temperatures. So you start usually at 500 degrees, and everything is well reversed, and you just see broad peaks. This is pure platinum. This is pure palladium. As you reach them, the palladium grows slightly, but not a whole lot. And it doesn't seem too much. Platinum comes into a lot, and when you see this sort of spreading in the peak, you know you're absorbing the T alpha 1, T alpha 2. This is not emerged into one peak. And that's the thing that very large crystallize. What's interesting is if you could impregnate platinum palladium, or you make a physical mixture, in both cases you form the bimetallic. So it doesn't matter what you do. You can mix them together, or you can just physically put them in the reactor, age it, and the peak and you can see shifting from that of platinum to somewhere in between. So this is the phenomenon that we call self-assembly. So in summary, addition of palladium improves both the durability and the reactivity. So it's a good thing, and we want to understand how it works and how to make it even better. So, first important fact, by itself, palladium is not very good for these reactions, for these oxidation. But it's there because it plays an important role. And it will improve the performance in some of the carbon oxidation, but not NO. So we want to know how exactly does that happen in actual reactions. Some of the literature is confusing. When you use bulk techniques like S-house, you may miss what happens on the surface of the catalyst. So when we started this work a few years ago, it wasn't clear whether in air the catalyst will oxidize and form a surface of palladium oxide. It wasn't clear that was really happening. Or whether it would be a phase separate. Both were possible explanations for what might happen in air when you heat on. So this study will be divided into 3 parts, and I will show you first what happens to the working catalyst. So the heating catalyst ages in air at 750, which is typically what we call by the GM group, the reasonable way to run all these catalysts. We compare monometallic and bimetallic catalysts. And we use 2 kinds of supports. The other one is to use this last stabilizer aluminum, and we also use gamma aluminum, just for comparison. And this was published in the Hansen. So, part 1 will describe the nature of what we see when we heat the catalyst in air at 750. In part 2, I will describe the process of self-assembly. And in part 3, I will describe how palladium slows the rate of sintering in this catalysis. So let's start with the first part. These catalysts are all cleaned at 750 C for 10 hours. And there is the aluminum support. Then you have palladium, you have platinum, and you have the bimetallic. The bimetallic, as I say, is roughly 1-to-1 the time ratio. Actually, we have a little extra palladium than platinum. So the first thing that we notice is if you use the platinum catalyst, it forms this nice, large, sharp platinum peak. If you use the palladium catalyst, you see nothing, because the palladium just remains well dispersed at this temperature. If you look at the bimetallic, it also shows a peak, and it's somewhere between the last constant of palladium and platinum. So this shows that indeed, if you have the platinum and palladium, and each them in air, both the platinum and the palladium now are becoming metallic. Whereas by itself, the palladium is not metallic, and it's an oxide. You can barely see it here, it's in the mass. So the message is, there's not a dynamically stable phase of palladium oxide. But in the presence of platinum, it is actually metallic and bimetallic. And that's the key to this catalyst. So, it turns out that particles grow so large, you can use SEM. So these are SEM images of palladium on the 2 aluminums and platinum palladium. And this is the different magnifications. But as we're just looking at the picture, you see the circuit that the palladium is quite well dispersed. But the moment you have both platinum and palladium, usually large particles. And this is the normal alumina that we use in the automotive industry for wash coating. So, your first conclusion, after looking at this, will say that platinum is inducing the later sintering of palladium. Because palladium and air don't sinter at all. It forms an oxide that is not volatile. Platinum does sinter, and that's what's happening. The presence of platinum is keeping the palladium metallic, and it starts to sinter. Okay, we can prove this by exams, so we know that if I just take palladium and aluminum and age it in air, it's all oxide. It matches the oxide. So hardly any reduced palladium at all. If I take platinum on the other hand, it is the 84 platinum standard. Aging air is all metallic. So aging platinum gives you only platinum metal in air at 750. Now if you go to metallics, there is the part of that palladium is reduced, and after reducing in hydrogen, it will reduce even further. So you can see that the palladium fractionates a little bit. There is a metallic phase and an oxide phase. What about the surface? I asked the question, what kind of surface do we have on the platinum palladium? It turns out it's very clean. There is no evidence of a surface oxide phase. So it is metallic platinum palladium. Right? And when we do TM, we actually start to see two types of palladium oxide on the sample. You can either have a highly dispersed palladium oxide that we can barely resolve in the microscope, and then you have metallic particles. These metallic particles are exactly what you see by X-ray diffraction and by X-rays. They are bulk. The coordination number is close to 12. So, you can see that the platinum palladium, these are metallic palladium particles. In addition, there is a little bit of platinum palladium oxide. And these are energy dispersal spectroscopy maps that allow you to see the dispersed phase is mostly palladium, and then the metallics have both platinum and palladium. What about a core shell structure? Do we see a core shell structure? We don't. Everywhere we look at these particles, the composition is nearly the same. And this is confirmed by exams because the correlation number of platinum neighbors to palladium and palladium neighbors to platinum. They're the same. So it doesn't make this problem. Okay. So, no core particles, no radiation, we can do maths and look at the surface layer, the medium surface layer, the bottom layer, and we can see that the composition don't change. So let's say that the palladium was a perfect alloy in the system. So the working catalyst in platinum palladium in air is like this. It shows metallic platinum palladium with a little bit of dispersed palladium oxide, that extra palladium oxide that leaves the one. Platinum by itself is metallic, palladium by itself is completely oxide, and you have to reduce it to make it metallic. So this is the nature of the working catalyst. Alright? So every slide segregation of palladium to the surface is negligible, and so the key message at the end of the day is platinum keeps palladium metallic under these conditions. Now the second part, how to self-assemble in a real catalyst. So we wanted to know if you take platinum aluminum and physically mix up palladium aluminum and heat it, how do they form these particles? Now you might think there could be particle migration. That is just as a teaser because this really doesn't happen. So this is an artifact. You only see that if you have a reactive substrate, and we talk about that later. So other than the liquid phase, where there may be some particle migration, you don't see much particle migration. So what's the mechanism? Something has to move. So we wanted to study that. We used the model TEN samples to develop the I-11 by Hansen and Burt group. And they also showed us an interesting reactor that's called the same review that allows you to heat samples very quickly and cool them down very quickly. So what we did, we prepared a model sample with the palladium oxide, and then we added a little bit of platinum. And then we just heated it to see what happens. So we started with pre-heal, crystal pre-heal, and we'll see here about 7,800 particles per square micron. So you can count all the particles. This is what they look like. They're irregular shape, exactly as we expect. flying oxide. Now, on top of that, we graduate some platinum. So the whole, which I said, probably 800 particles. Now, it's difficult to separate the platinum and palladium, but you can see that the graduated platinum divided over 100,000 particles of platinum. And those are the blue specks that you see. So here, you can say, yes, that's platinum, that EBS you can confirm. So we have a physical mixture, but at very short range. Platinum particles next to palladium oxide. Alright? XPS confirms, yes, we have palladium oxide. What next? We heat it up for 2 minutes. That's 650 C. So same sample, heat it 250 C, and miraculously, all those platinum particles go on. They disappeared, and what has happened is they have migrated, the platinum has migrated, and converted the palladium oxide into metallic palladium in air, in flowing air. And we see that change in particle size distributions, that large piece of platinum is gone. So this is the origin of self-assembly. So the self-assembly of platinum palladium catalysts involves a mobile platinum species that reacts with palladium oxide, reduces it, and then becomes platinum. So it's a self-healing process in the real volume of catalyst. You can confirm that XPS, indeed, you have reduced the palladium oxide to metallic palladium corresponding to the alloy. So you made the alloy in situ. Now, of course, we do this at 620 C in real life catalyst, in real life temperature. We want to prove this is not just happening on all catalysts. We did the PGA, where we did palladium acid and palladium oxide, aged it, and indeed we saw the reduction. It's slow, so we had to hold the temperature constant to let the weight drop, and we could confirm that the weight change was consistent. And we can go from the dynamic calculation and go our phase diagram. We know that the oxide is going to be stable at higher pressures and lower temperatures. The metal is going to be stable at high temperatures and low oxygen pressure. This is how the liquid pressure. And you can see that mixing platinum oxide with palladium oxide, you have lower the reduction temperature and form a biometallic. Okay. So, in summary, you start with an oxide, you add platinum nanoparticles, and you heat in air, and you get a biometallic. And it happens very quickly, and it happens inside the catalyst. Alright, so that brings me part 3, and the remaining 5 minutes that I want to now tell you what the platinum actually do in the real catalyst. So I show you the device that we activity and ruled out particle migration. So now remains the question, the volatile species or the mobile species, are they platinum only? Does palladium also move? Is there a mobile palladium phase? And how does this growth involve a liquid phase process or a solid phase? And these kinds of questions you cannot answer on the real catalyst, because you can do a cross-section on the automotive catalyst at the initial stage, after aging. Now you can say, yes, there's a lot of synergy going on. But the auto catalyst that comes included right over here allows to see the same region of the catalyst after heating air to 790 degrees, whatever you want, your active microscope, you can see that this is really all happening. The particles are disappearing, you can overlay the image one on top of each other, and there's hardly mobility at all. The level of mobility is associated with the spin tune, not the perfectly stable, so there's a little stretching going on. But other than that, so we use the one catalyst approach. I want to show you our reactor system. So for these one catalysts, we use a thin film of silicon nitride, which is in an EM grid. That grid is created based on this reactor. This is the saber tube. It is heated resistively, so we get heating rates of 100 C per second. You can heat up very quickly, you can cool it up very quickly. Alright? So let's see what happens on all catalysts. You heat palladium, and very quickly it forms an oxide. The nice spherical particles become irregular in shape, and after we can see very little change in particle size distribution. Whatever change happens in the first 2 minutes. That's when you see a big change in the number of particles dropping. After that, it's pretty stable. Okay, palladium oxide is very stable at 800 degrees. Now what happens platinum and palladium? So if you do platinum, you see aging, very rapid. At 650 C, 2 minutes already, a big change in the particle size distribution. And by 750 C, you start to see a little bit of bimodal distribution, some small particles and some large particles. That will happen with platinum palladium. So platinum palladium, very well behaved, regular, uniform size distributions. So palladium does go to radioactive center. How does it do it? Now you can argue it blocks or prevents the emission of platinum atoms. And that's ultimately what we concluded. The concept was looking at the mechanistic details. So this is platinum oscillator. Here are 4 atoms. Some particles disappear. Look at the black box. Some of the particles are gone. Some of them are larger in size. So classic phosphorylating for platinum. Now what about platinum palladium? You see exactly the same phenomenon. So if you cut this box, look at this one here, some particles completely disappear, others are grown in size. So the mechanism is the same. You know that platinum forms a mobile oxide. What about palladium? Can it also migrate? These results show that yes it can. Both palladium can migrate on the surface of silicon and so can platinum. And the palladium only happens if you start from a metallic particle. To start from an oxide, it doesn't move because PDO is not volatile. Platinum palladium, however, does show similar behavior. You do some DAP calculations to find out is it possible, what is the barrier for emitting platinum in the form of an oxide. So if you emit platinum oxide and put it in a support, the barrier is quite low. You put it in the vapor phase, the barrier is higher. So of course, this is the latter part of the story. Vapor phase processes become important at high temperatures and low temperatures. It's all surface diffusion. What about platinum palladium? It turns out both platinum as well as palladium could be emitted at the temperatures we're talking about. We don't know the species involved, we don't know exactly what migrates, but we can tell that a platinum palladium particle completely disappears, so it doesn't leave behind palladium. Both of those migrate. So the last part was, what about the vapor phase? Does anything go to the vapor phase? So these samples are perfect for looking at the vapor phase transport because we are full of air. So if anything is emitted, we will lose mass. And we can measure carefully the mass by energy dispersion spectroscopy, by using microprobe analysis. If we take palladium, and here we put 5 angstroms of palladium total. So that's why I say 500 picometers. So this is showing you the amount of palladium on the sample. Of course, it's in the presence of foreign particles and not in the internal. What happens after heating palladium degree? No loss at all. So palladium is not immune to the vapor phase. It forms an oxide that is involatile. What about platinum? We put platinum and we do the same experiment. If you just look at these shaded regions, they're telling you the story. Platinum is lost. So it means significant amount of platinum as if your air was listening. So platinum forms a volatile oxide and at higher temperatures, particularly 800, you lose the water to a vapor phase process. Okay? What happens when you add palladium? Palladium slows this rate of emission. So here are the results for the platinum palladium, and here it's complicated because some of the changes are called by particle size distribution, but bottom line is only a 10% loss of platinum from this platinum. So we see changes in composition over time, and they're associated with a loss of platinum. So these are particle size distributions. We can go on. So why does palladium modify the molecule to the platinum? It could be possible that it forms a shell, but it doesn't. I showed you that here there's no such structure. So what really is going on is you form the biocarbon. Sometimes there's room for a phase segregation, but by and large you have a metallic platinum palladium. And why does it have a lower vapor pressure? It's a reality. The solution is not ideal, but the deviation from reality is very small. So 50-50 platinum palladium would have a 50% reduction in the rate of emission. So we are cutting down the emission, and at this point it suggests that the surface diffusion, both species are moving, which is why as the particles grow larger in size, the composition stays the same. We do not see phase segregation, and that is the reason why this catalyst works so well, because we think this is the crux of the matter. The palladium oxide is like a trap. It is trapping the monohydrate species and preventing them from going into vapor phase. And thereby, it slows the rate of sintering by keeping these platinum palladium particles. And in fact, these platinum palladium particles now, the question is what exactly is the effect on emission? Is still spreading this oxide more in detail? That's what we know for sure. And so we acknowledge my co-authors on the paper, the PhD work of Time Jones, Christian's the PhD student working on it now. We have also Andrew, XPS through Catalina, William, and Shiva. I think it's a postdoc is here also in Rome at San Diego. So that is our team funding competitive from the National Science Foundation, some funding from Ivy Fellowship for our time, higher grant that allowed us to interact with the Hansen group, and in the end I'd like to thank you all and congratulate Rostrup-Nielsen for leading us in the direction that we followed over those years since we first met. Thank you.
Before questions, I just want to remind you, our honoree is going to fill in the cancer presentation, so don't run off, you'll be giving a presentation. Questions?
Yeah, very interesting presentation and very exciting results, but I would like to remind you that even though you have an ideal solution at alloy formation, still you have to deal with the surface energies and surface enrichment due to the relative volatility differences between the two metals, dictated by their differences in their melting points. So you might just have nice bulk alloys, but still the surface may be enriched by palladium. I was just curious if you could distinguish that criteria.
We know the best we can. We can keep the catalyst aged in air and look at the surface region. We don't see any segregation, we don't see an oxide formation. We've done X-APS and we look at the average coordination of platinum and palladium. They're very similar, suggesting the particles uniform. So we're not convinced that there's a whole lot of segregation of palladium. Now, how it quantifies the rate of emission, we don't really know. Our simple hypothesis is alloy. There could be other factors responsible. So I believe in the gas atmosphere, all of that can play a role. So we don't know it. We don't know all the answers.
Yes.
So your studies on the motor support were on the silica support, number one, and then I presume the practical catalyst is on an alumina-based support. So to what extent the nature of the support shall have an impact on your observations and conclusions?
Yeah, it's a good question. The practical industrial catalysts are aluminum. So what I did was I showed you first that we did the studies on aluminum and found out what is the rate of growth of particle size on aluminum in each of those cases. Then we did a long study and compared the behavior, and it was very similar. So in this case, over this range of conditions, this is a reasonably good model to study this phenomenon. Of course, we can convert it into aluminum, we can do lots of things. There's a lot more to do, but I think as an initial guess, the silicon oxide thin film on silicon nitride is a really good substrate because it doesn't charge on the microscope. You can heat it to 1,000 degrees in air and it solves all the problems of electron beam damage because you do water treatments in the reactor. In and then engage my effort only to take pictures. So it's a very different way of doing time-lapse studies. Bob?
One more.
Thank you for this beautiful presentation. It reminds me of very old work by Yermakov, which was using metal molybdenum to anchor palladium particles. And I'm wondering how little palladium you can get away with. Actually scale with the amount of palladium this effect.
Right. I think it's a good question. We haven't thought of this as anchoring because we found we were huge. We grew up in 20 nanometers. So if there was something at the interface between the animals and the board, it would be small modular. Here, it's more about a trap. I showed you palladium oxide is just acting like a trap. Any more ion is captured and it becomes part of it. And if you extend it to that other work, they can have partly dispersed species on the surface, and that's obviously the direction we are going. Thank you.
Thank you very much, Bob. And next speaker will be the honoree who agreed to fill in for those who canceled.